Now that we have learned about Newton's third law, which is for every action there is going to be an equal and an opposite reaction, or in other words, force always occurs in pairs, right? When object A exerts a force on object B will respond or react by applying the same amount of force in the opposite direction on A, right? Now let's try to quantify that and see where that takes us to. So let's take the example of two objects. Now I'm going to call these as A and B. And A travels, object A. The object A, let's consider the object A has a mass of, let's call it ma, and this particular object is traveling with a certain velocity, and then let's call it, the velocity as ua, right? And similarly, let's consider another object which is B, and let's consider this the mass of this object to be mb, and let's consider that this object is traveling with a certain velocity of uv to begin with, right? So let's consider this scenario. I think there is a slight lag here, but what's going to come up here is this object is traveling with a uniform velocity of ua, and this object is traveling with a uniform velocity of ub, and the mass of this object is ma, and the mass of the second object is mb, right? Now, what will happen if these two objects collide, right? If object A hits object B, right? What will happen at that point in time, right? Now, what you're saying here is when this object and this object touches one another, when A and B touches one another, right? What will happen? If you apply Newton's third law, object A is going to apply a force of certain force. Let's call it force AB, FAB, which means that that will be responded by object B in the opposite direction. This will be the reaction, and let's call it an FBA, right? So this is the action, this is the reaction when they touch each other, right? And what will happen? Of course, because each of them, this is an external intervention on each other, right? Which means that their velocity would change, right? Because it's an external intervention, the first law states that the object's velocity is going to change, and let's assume that after the collision, object A starts moving with a velocity of VA, and object B starts to move with the velocity of VB, right? Let's take this as a scenario here. So you have two objects started with our initial velocity of UA and UB with of mass MA and MB, and they collided, which means that there was an action and a reaction force in the opposite direction, and after that, because there is an external intervention on both of them, the velocity changed, and the changed velocity is object A started to move with VA, and object B started to move with VB. Now Newton's third law states that FAB equals FBA, right? Every action has an equal and an opposite reaction, right? So this is Newton's third law. Now what is FAB? Now if you see FAB is nothing but the force applied by A, right? Which is the mass of A times the change in velocity of the rate of change of velocity of A, right? That is the momentum, right? So ma times VA minus UA over T, right? So this is your this is force AB, right? What is applied by what gets applied by A. Here is the mass times the final velocity times the initial mass minus the initial velocity over T. Similarly, FBA is going to be equal to M of B times VB minus UB over T, right? And T is that brief period of time when they had actually collided, right? When they were in touch, so when the force had actually acted, when the action and reaction had happened, that is what is that time T. Now, if you really equate these two into this equation, you know that this T is a common denominator, so we can ignore this. Now, let's see what happens. Now, when you replace FAB with this equation here, so what I get is MA VA minus MA UA is equal to, here it's going to be minus, right? So which becomes like, MB UB minus MB VB, right? So I have applied this minus into this equation. Now, if you rearrange this equation, what we will get is MA UA plus MB UB is equal to MA VA plus MB VB. So this is what you get. And if you notice this here, all these terms, if you see the left hand side, right, this is the initial momentum of the first object, which is object A, and this is the initial momentum of the second object, and this is the final momentum of the first object, and this is the final momentum of the second object. So where Newton's laws have led us to is, it says that the momentum, the momentum of the objects are actually conserved. That is, although the velocity changes for both of these objects, the velocity of A changes from UA to VA, and the velocity of B changes from UB to VB. All those happens, but unless there is no external, when I say external, nothing outside of these two objects. There is no object C that is coming and interfering with these two. It is just A and B are interacting with one another. In such an environment, the momentum of both the objects are going to be conserved, right? So this is what is called as the law of conservation of momentum. Law of conservation of momentum. So this is preserved. The momentum is preserved in an isolated system. When you say isolated system, it is the system that only has E and B. There is no object C, or there is no object B or anything that is going to interfere. It is isolated. It just has A and B, and within that, the momentum is going to be conserved. That the sum of their initial momentum will always be equal to the sum of their final momentum. Now, before we move on to the next thing, the exercises, I think we have covered all the concepts, but there is one last thing I think we should be clear on. And to understand that, let's take the example of a friend in a swing, right? So let's take that you have there is one subtle aspect about inertia, so we will clarify that as well. So let's take that consider your example of you have one swing where you have two friends, and and both of them are sitting on two different swings, right? So let's take that example here, and that let's take your of the two friends, one friend is a little bulk is heavier than the other friend, and both of them are sitting on a very similar swing. Now, which means that and both of them are at rest on that swing, and if you had to give them a push and make them move, would it be the same amount of force that you would apply, or would your force going to be any different? Obviously, your friend who's heavier, you've got to apply more force for that person to start swinging, but whereas you may not have to apply as much force for your other friend who's relatively leaner, right? Which means that for you to get them into motion, you got to alter their disturb their inertia so that when they are so that their velocity changes from zero because they are at rest and start moving in that swing, and which means that your force is going to also be different on both, which in a way implies that your inertia is related to the mass of your frame of that particular object, right? An object with higher mass is going to have higher inertia, and an object with smaller mass is going to have smaller inertia. So inertia of an object depends on the mass, and those two. I want you to be clear about that relation between inertia and mass, and that will come in handy as we solve problems in our next section.
One final thing before you leave. If you wish to revise the concepts that you've just learned, please look up and try out the free Revise app bot on Telegram app. Telegram is available for free on both iPhone and Android. Also, if you did like the content that you just watched, please do like, share, and subscribe this with your friends. Thank you.